Hello everyone again. This is lecture number 4 on motion in a straight line. In the previous discussion, we have completed with deriving all the three important kinematic equations. In the last 10 minutes, we were understanding the derivation using the calculus. The first was quite clear. The second, I will try to explain again, and then we can move on to the third one, and then we can move with the further discussions. Okay. So I'm Samir Lawankar. Let's begin our discussion. Okay, so right now we are on the sixth point here, that is kinematic equations for uniformly accelerated motion. Before this, we have completed the introduction part, the position, path length, and displacement part. Then average velocity and average speed is explained. The instantaneous velocity and speed is also explained, and acceleration has also been explained quite clearly. Okay, so kinematic equations, we have derived all these kinematic equations right now, and we are understanding the calculus, how to derive those with the differential calculus, basically calculus, and then we will understand the other different concepts. Okay. So this is explained. Okay, so let me just derive this again so that this will be again clear. Okay, so let me first derive the left hand side. So this is nothing but integration of x0 to x dx. Okay, so this is nothing but it is 1 times dx. So this is equal to x from limits x0 to x1. Let us see. This is equal to final value minus initial value. Okay, so that is the derivation of the left hand side. On the right hand side, what we will do? We will do integration of 0 to t v0 plus at dt. We will separate those terms. This will be equal. This will be equal to 0 to t v0 dt plus integration 0 to t at dt. Okay, separating more, v0 can go outside. This will be equal to v0 integration 0 to t dt. Why it can go outside? Because v0 is a constant value plus integration 0 to t. So this is one of the rules that if it is constant, then it can go out. Okay, so it's 0 to t a times 0 to t dt. Okay, so therefore similar terms we can write this as equal to v0 t from 0 to t plus a times t square by 2 from 0 to t. Okay, just putting the values, you will get this is equal to v0 into t minus 0 plus a into t square by 2 minus 0 square by 2. Fine, so that will give you v0 t plus half a t square. Because 0 it is 0. Okay, so that is how, and as the left hand side was x minus x0, this if you are putting x0 to the right hand side direction, you will get this is equal to x is equal to x0 plus v0 t plus half a t square. So that is the derivation for your second kinematic equation. Let's move on. So now for the third equation. So now a new rule, new difference, a new one of the more concept of differentiation is being used up here. So that thing says that a is nothing but equal to dv by dt. This is being known. Okay, so now this dv by dt can be also written as, okay, so now for now you can understand this as fact only. When differentiation will be understood in mathematics, this will be very clear to you. Okay, so this can be written as dv by dx into dx by dt. So basically we are adding and multiplying the terms which can get cancelled. So dx and dx can get cancelled, but this will be equal to dv by dt. Okay, but here we know that dx by dt is nothing but v. So it is v into dv by dx. Okay, now just do the integration again. So what we will do, we will just do integration of v. So just 1 minute. So this can be changed into, so this equation can change into v dv. This equation can change into v dv is equal to a dx. correct? So dx can go in this place, and this will be equal to v dv equal to a dx. Okay, so now after this, just integrate v dv from so okay, I will tell the limits later, equal to a dx. Okay, so now what will be the limit of v? V will go from v naught to the value of v. What will the limit of x? X will go from x naught to x, correct? So I have already explained to you what is the integration of t dt from, let's say, t1 to t2. This will be nothing but equal to t square by 2, right? So it's nothing but t to the power n plus 1 upon n plus 1, as the value of n was 1 before, so it's 1 plus 1, that is 2 upon n plus 1, which is again 2, in limits t1 to t2. So just put those values, so it's nothing but t2 square minus t1 square, like this. Okay, so it's nothing but t2 square minus t1 square by 2. Fine. Similarly, if you do for this location, we'll get this is equal to nothing but v square by 2, that is v naught to v, which is equal to a can come out, which is equal to x naught x a dx. Okay, so this will change it to v square minus v naught square, final minus initial. So we will put v value only here for the final direction, for the final point, upon 2, which will give you a into x minus x. Okay, now just doing simple mathematical manipulations, you will get this is equal to v square, which is equal to v naught square plus 2 into a into x minus x. So that is how, using simple this is if you will understand, when you will go into clear depth of differential calculus and methods of calculus, this is the simplest things which you are trying to understand. Okay, t dt, a is equal to dv by dx, dv by dt is changed to v dv by dx, etc. Okay, so I tried to explain to you as low as I can. So please, if you cannot understand this, please go and rewind this lecture again, and this will be clear to you. Okay, so finally the three equations are being understood, three equations are derived. First, using simple methodology, simple mathematics, using our concepts of your area under curve, etc. And now we are deriving this using method of calculus. Okay, so the advantage of this method is that it can be used for motion with non-uniform acceleration also. So what will happen, let us say this a will be here constant now. So what we did was we put a outside this. There may be a situation where this a is a function of x. Okay, so if this would have been a function of x, then there would have been a multiplication, like let's say x dx, or let's say x square dx, some sort of that would have happened, and then we would have integrated here. Similarly, what would have happened, let us say here also. Okay, so it's a t dt now. So here what would have happened, let us say if a would have a function of t, then we would have took out a outside this integral position. We would have took out a outside this integral position. We would have kept it inside only. We would have changed it into this function, and then we would have used some of the rules of your integration. Okay, so that is one of the advantage of using method of calculus here. Okay, so the advantage of this method is that it can be used for motion with non-uniform acceleration also. Okay, fine. So now let's look at some of the examples so that to clear our mind regarding all these concepts. Okay, so sign convention is a very important topic here. If the sign convention is understood to you to very, very detail, then 95% of the questions have been done. You won't make any mistake here. Okay, so let us understand each and every question. Okay, so let's understand a ball is thrown vertically upwards. Every word is important. Okay, so it is thrown vertically upwards with a velocity of 20 meters per second from the top of a multi-story building. Let us say this is the position from where we are throwing the ball. Okay, so this is the initial velocity given. So v naught is equal to the velocity is ball is thrown upwards, right? If we are taking upward direction as positive, downward direction is negative. Therefore, the velocity will be plus 20 meter per second. Clear? Okay. The height of the point from where the ball is thrown is 25 meters from the ground. Okay. So that this is the location, this 25 meter is given to you. Okay, now how high will the boil sorry high will the ball rise? Okay, so let us first understand what is happening here. Okay, even if we are standing at some location and we throw a ball upward, using because there is a gravity acting, there's a gravity force, gravity acceleration acting in the downward direction. With any force, when we try to send the ball upwards, because of this negative acceleration happening, the velocity of this ball will keep on decreasing and it will finally reduce to zero. The point at which it reduces to zero is the maximum point that the ball can rise. Okay, so that was the explanation of this first. Let's not read below. First of all, let us understand this only. The value of g is given to you as 10 meter per second square. That is the value which you need to take for your calculation purpose. Okay, fine. So let's start with the first solution only. Let us look over to the second solution after second question afterwards. Okay. So let us take the y-axis in the vertically upward direction with 0 at the ground. So we are taking 0 at the ground here. Okay, so any displacement which will occur or which we will find will be from this location here. Okay. So let us take the y-axis in the vertically upward direction with 0 at the ground as shown in the figure. So now v0 is given as plus 20, which I just explained to you also why it is plus 20. Sorry. So v0 is equal to plus 20 meter per second. Okay. Next thing is please remember that because acceleration is downwards. Okay, because acceleration is downwards and we are considering positive direction to be upward direction. Therefore, this a value will be minus g. Fine. So this minus g will be equal to minus 10 meter per second square. Okay, so that is how this thing is being explained. Now let us move to the next point, that is v. So final velocity v is nothing but v final only. This v is nothing but v final. What will be the final velocity? Final velocity will be 0. I just explained to you, because that will be the value at which the ball will rise and will stop. Okay, that is the maximum distance which you need to cover. Okay, now if the ball rises to a height y from the point of launch, how to explain this now? Okay, so as we are accepting every location from this point, let us say that we are accepting that this is the highest point which is launching, and from ground this location is y. Okay, then using the equation, let us use the equation now. What is the equation we used? We used equation v square is equal to v naught square plus 2ay minus y naught. Why we use y minus y naught? First of all, as the displacement is in positive direction, therefore this will be plus. And second thing is the displacement only occurred in this location, right? What is the y naught value? Y naught value is given to us in the question, which is 25. Okay, so let's just put everything here. Let's just put everything here. So so v square. So final value of v square is, that is 0 square, which is equal to what? Which is equal to your v naught square. V naught square is given to you as plus 20 squared plus 2 into a value is minus 10. Please remember, into y minus y naught. Okay, this should not be x minus x naught. This should be y minus y. Okay, therefore, just simple calculation will lead us to y minus y naught will nothing but equal to 400 by 20, which is nothing but equal to 20. Okay, therefore the displacement is also positive direction. That means our sign convention is correct. Our answer is also correct. Okay, so therefore what we got, that the maximum height that the ball will rise will be equal to 20. Okay, so that is the explanation for the first point. Okay, now let us move to the second question. The second question says that how long will it be before the ball hits the ground? Okay, so what does it mean? It basically means, okay, so what is actually happening? The ball was here. Now the ball went upward. It reached here. The velocity was 0. Now it is under free fall. It is under free fall. Why it is under free fall? Because only acceleration due to gravity is happening on this and no other force is acting. So now they are just asking the time it took for the ball to hit the ground. So some time would be took up here. Some time would be took up here. The answer is being required just t1 plus t2. Fine. Question is understood. Now let us try to understand the solution. Okay, so this question can be solved in two ways. Okay, let us first understand the first method, then we'll move to the second method. Okay, so in the first method, we split the path in two steps. Okay, so there's a similar thing which I just said. So first of all, we will just try to calculate the value of T1 from A to B, and second time we'll try to calculate the value of B to C. Okay. Okay, let's calculate. So the upward motion A to B and the downward motion B to C, and calculate the corresponding time taken from T1, corresponding time taken T1 and T2. Okay, so since the velocity BB is 0, now what we can do using the first kinematics equation, we know that VB is nothing but equal to VA plus A into T. This is T1 which we are calculating, correct? What is the final velocity? Final velocity is 0. What is the initial velocity? Initial velocity is plus 20 given in the question, plus A time. What is A? A's value is minus 10 into T. Okay, simple calculation gives you the value of T1 is nothing but equal to 2 seconds. Fine. So this is the first calculation which we got. Keep this aside and start calculating second thing now. Okay. After this, now this is the time from going from A to B, that is 2 seconds. Now from B, what will happen? At the point of maximum height, this is the point of maximum height, the ball falls freely, which I just explained. So only acceleration due to gravity would be acting on it. Now the ball is moving in negative y direction. Quite evident, it is moving in negative y direction now. Okay, so now let us use this equation. Y is nothing but equal to y naught plus at plus half a t square. Please remember here t will be t2. Here also t will be t2. Now let us calculate this displacement. Okay. So now this displacement y will be nothing but equal to initial value of y naught. Initial value of this value of y is only required, right? This value of y is only required. What is the value of y naught? Y naught will be equal to 20. Y minus y naught is 20 meters, and y naught is given to you as 25 meters. So y minus y naught is 20, right? And what else? Y naught is 25. Therefore, y is nothing but 40. Okay. So therefore, now this time just understand this question. Okay. So y is nothing but equal to initial value of displacement plus initial velocity into time plus half a t square. Okay, so here please understand what is the initial value of the displacement. What is the initial value of displacement? The initial value of displacement is this location from the original position. What is that value? That value is 45. Okay, keep on understanding each and every concept. What is the initial value of displacement from the reference point? It is 45. It is in positive direction, therefore this will be plus 45. No minus sign will be used. Okay, if the movement is negative, there is no use of that. Keep on understanding each and every word from the initial definition only. Initial value of displacement is plus 45. Okay, now next thing is plus. Okay, what will be the value of final displacement? Final displacement will be 0. Final displacement will be 0. Fine. This will be T2, this will be T2. Okay, what is the initial value of velocity? Initial velocity is 0 multiplied by T2, so just ignore this, nothing to be understood here. Plus half into what is A? A will be minus 10 and T2 square is unknown. Okay, so just using this, you can understand. So finally, this is nothing but T2 square is nothing but equal to 45 into 2 by 10. So that will give you 90 by 10. Which is 9. So therefore we will get T2 is equal to 3 seconds. Fine. So you got T1 is equal to 2 seconds, T2 is equal to 3 seconds. So the amount we took from this to this was 2, and the amount took from this to the final location was 3. Okay. Therefore, solving this, we got T2 is equal to 3 seconds. Therefore, the total time taken by the ball before it hits the ground is T1 plus T2, which is equal to 2 seconds plus 3 seconds, which is equal to 5 seconds. Okay, that was the second B part which was being asked. So now this is the first method. Now let us understand this by a second method. Okay, the total time taken can also be calculated by using or by noting the coordinates of the initial and final positions of the ball with respect to the origin chosen and using this equation. Okay, so now let us use this equation again and try to just use the definitions of each of these concepts. Okay, so y is equal to y naught plus p naught t plus half a t square. Okay, here time which will be obtained will be final time only. Okay, understand each and every point clearly, very easy to understand. Okay, what is the final position? Final position is this. So final value of displacement is 0. What is the initial position? Initial position is this, that is 25. So it is 25 here. What is the initial velocity? Please remember here, initial velocity was in this direction here, right? That was equal to plus 20. So we will add this as equal to 20 multiplied by t. Fine. Moving on, plus half into minus 10 into t square. Okay, solving this, you will finally get a quadratic equation which is the greater than, that is equal to 5t square minus 20t minus 25 equal to 0. Okay, just try to solve this equation. You will get answer as equal to t is equal to 5 seconds. Okay, so only using simple calculation also, not even trying to do it 2 times, you got the answer directly as 5 seconds. Okay, so if you understand the sign conventions clearly, if you understand the displacement concepts, the velocity concepts, where to apply it, what is the final value required, what is the initial value required, this question can be solved directly in 10 seconds. Okay, as far as you can understand, if you can just do this quadratic equation solution. Okay, for solving this quadratic equation for t, we get t is equal to 5 seconds. Note that so quadratic equation can be solved, you know, minus b plus minus under root b square minus 4ac upon 2a. So let's use it directly. Okay, so note that the second method is better since we do not have to worry about the path of the motion, as the motion is under constant acceleration. So just because this complete question is being asked in constant acceleration, it is quite clear, because directly using the different concepts of kinematic equation, using the concepts according to our choice, it makes it very easy to understand or tackle the situation quite nicely. So I suggest you to solve many questions regarding this concept. Try to have a quite strong grip on understanding when to put plus, when to put minus. Try to decrease the number of steps so as to make your concept more and more clear. Okay, so I would suggest you to solve the questions, try to solve the questions if they can be solved in 2-3 ways, so that the concept will be much more clear. Okay, fine then. So this question is completed. Let's move on to it's an example, but we'll understand the complete discussion about free fall. Okay, what is a free fall? Free fall is basically when there is no force acting on an object on its movement downwards, only and only when the acceleration due to gravity is acting on the object. Okay, as far as you're understanding that there is no air resistance happening. Okay, so basically there is no external force happening apart from your acceleration due to gravity or gravitational force. Okay, let's move on. So only acceleration due to gravity is happening, nothing else is happening. Okay, so free fall, discuss the motion of an object under free fall, neglect the air resistance. Okay, so this is also a concept only, but this has been put as an example. Okay, so an object released near the surface of the earth. An object released, please remember, this is also very important point. It is released almost near the surface of the earth only. Okay, the amount of release or the displacement which is happening is very small as compared to radius of the earth. Okay, if this would have been very large, then the amount of the question would have changed. Why? Because the gravitational force is not always constant with the change in the height. This concept will be much more clear when you will understand the chapter of gravitation. Okay, so let's not go into that chapter right now. We will understand this at a later stage. But this complete motion of free fall is only and only valid. And first of all, we are neglecting the air resistance. And second thing is that this amount of displacement which we are finding or which we are considering is very less than capital R. Fine. So an object released near the surface of the earth is accelerated downwards under the influence of the force of gravity. Quite evident. The magnitude of acceleration due to gravity is represented by g. So this is small g. Small g is basically used to calculate or to represent the magnitude of acceleration. If air resistance is neglected, the object is said to be in free fall. So this is the terminology which is given, that if the air resistance is neglected, then this object is said to be in free fall. Okay, when it is under the influence of force of gravity. If the height through which the object fall is small compared to Earth radius, which I just explained to you, that if the delta x is less, or that delta y is, or that y is basically less than, very less than Earth radius, that is capital R, then g can be taken to be constant, equal to 9.8 meter per second square. Free fall is thus a case of motion with uniform acceleration. So this is also a case of uniform acceleration, and because this is a case of uniform acceleration, you can directly use all the kinematic equations here. Okay. So that being said, we assume that the motion is in y direction, more correctly in minus y direction, because we choose upward direction as positive. Okay. So here the motion is y direction, more correctly in minus y direction. So basically, because let us say we understand everything which is going upward as plus y, everything which is going down is minus y. So here the free fall is happening downwards, and hence this motion is happening in negative y direction. Okay. So we assume that the motion is in y direction, more correctly in minus y direction, because we choose upward direction as positive. Okay. Since the acceleration due to gravity is always downwards, it is in the negative direction, and we have a is equal to minus g, that is 9.8 meter per second. Okay. So let's not complex the issue, because sometimes I won't even try to say that a can be taken as plus g also, because the sign convention would change. But let us be very clear, because we are starting with the basics of every chapter. So we are understanding that a is equal to minus g, and we are keeping this sign convention in mind. Okay. So a is equal to minus g, which is equal to 9.8 meter per second square. Sometimes you also approximated to 10 meter per second. Okay, fine. So the object is released from rest at y is equal to 0. Okay, so let us say that it is being released. So let us say we are taking this to be the origin point. Y was 0 here, and this was the object. We released it. Okay. So now when we are releasing it, the value of initial velocity will be 0 only, because there is no force acting, there is no velocity being imparted into it. When it is imparted, first of all, what was the first kinematic equation? It was v is equal to v naught plus at, right? What is the final velocity? Final velocity at some time will be v naught will be 0 plus this will be minus g into t. So this can be written as this is equal to minus 9.8 into t. Firstly, okay, understanding the second line. So next, what is the second point here? Second point is y is equal to y naught plus v naught t plus half at square. So what will be the displacement? Initial value of y is given as 0. It is 0 plus initial velocity is 0, again 0 plus half minus g t square. 9.8 by 2 will give 4.9. So y will be equal to minus 4.9 t square. The second relation is here. This is the second relation. Okay, please remember these relations are only and only valid when we are taking y to be y, initial velocity, initial displacement to be 0, and the initial velocity also to be 0. Okay, so if the frame of reference changes, then the value of y will also change, and if the velocity is also there, then velocity will also equal. But free fall generally has velocity 0. Free fall also always have velocity 0. Generally, if it is in free fall, only especially due to force acting, then we are considering that initial velocity should be equal to 0. Okay, only acceleration due to gravity is happening. Okay. For the third relation, what is happening? It is v square is nothing but equal to v naught square plus 2 area, sorry, not area, y acceleration y minus y naught. Putting it again, so v square is nothing but initial 0 squared plus 2 into minus 9.8 into y minus 0, which will give you the answer as final velocity squared is nothing but equal to minus 19.6 into y. That is being written. Okay, why does it have a unit of meters per second square? because this is velocity. So this velocity is nothing but equal to meter per second whole square, which will give you meter square second to the power minus. Okay. So this not anything else to explain. Here is no, fine. That's all. Okay, let's move on. These equations give the velocity and the distance traveled as a function of time. These equations gives the velocity and the distance traveled as a function of time, and also the variation of velocity with distance. So that you can see just everything which is written here is being written in a theoretical format. Okay, in this slide. So basically, we can find a relation between velocity and time, displacement and time, and velocity and distance. Okay. Variation of velocity with distance. Okay. The variation of acceleration, velocity, and distance with time have been plotted in figure A, B, and C. Okay. So now let us understand everything which is written here. Okay. So basically what they are just trying to tell here, let me make you understand if I can. So let us see the first relation. Okay, so it's minus 9.8. So as you can see, there's a constant value that's going downward and downward. Okay, if we can understand y and t square, because y is a function of t square, you can understand that this will be a non-linear curve. Okay, so it's going like this, and then as as b is nothing but equal to minus 9.8 into t, then the slope of this will be dv by dt, which will be equal to minus 9.8. So the acceleration will be constant always, right? If acceleration constant, then acceleration will be always straight. That can be explained from this step. Fine. Okay, so these were the explanation. Let's move forward. Okay, so a new example now, that is Galileo's law of odd numbers. Okay, so the distance traversed during equal intervals of time by a body falling from rest stand to one another in the same ratio as the odd number beginning with unity. The question can be quite tricky to understand, but as we move forward with the solution, you will understand. This is also a discussion only, also a concept to be explained only. There is nothing sort of example to be explained, but because these all things are very easy to understand using examples, that's why these are put forward as examples. Okay, so what does he said, that when we try to find the distance traversed under a free fall, what we found out, let's say that the body falling from rest and to another in the same ratio as the odd numbers beginning with unity. Okay, so for the same time interval, when we are trying to find out the value of the displacement, those were in the ratio 1, 3, 5, 7. Okay, now let us try to find this value. Okay, so let us try to prove it. So let us divide the time interval of motion for an object under free fall into many equal time intervals tau. Okay, so what is basically happening? This was a ball. Let us say that in some time interval it reached here. Let us divide the time intervals into equal proportions like this. So this was tau, this was tau. Okay, this cannot be the actual representation. The actual representation is some sort of this. This is your x1, x2, x3. You can understand this also as the acceleration is acting downward and downward, the velocity is increasing. If the velocity is increasing, then the displacement will also increase, right? Because the time period is constant. So here also the time period was tau only. Here also the time period was tau only. Here also the time period was tau. Okay, so now we are just trying to find out that the ratio of x1 to x2 to x3 to, let's say, x4 dot will be 1:3:5:7. And that is why it is called as your law of odd numbers. Okay. So let us divide the time interval of motion of an object under free fall into many equal intervals tau and find out the distance traversed during successive intervals of time. Since the initial velocity is 0, so v0 is given to u as 0. Therefore, what we can say? We can say that y is nothing but equal to y0 plus v0 t plus half a t square. We are also assuming y0 to be 0. Therefore, this will be equal to y. v0 is 0. That is nothing but minus half g t square. Okay. Using this equation, we can calculate the position of the object after different time intervals. Let's say we can calculate the value of displacement occurring at 0, tau, 2 tau, 3 tau, etc. So from here to here, it will be tau. From here to here it will be 2 tau. From here to here it will be 3 tau. Correct? If we take, so now let me rub this. Okay. So now if we take, which are given in second column of the table. So as you can see that this is the time period we are taking. So it's 0, tau, 2 tau, 3 tau, 4 tau, 5 tau, 6 tau. Just putting the values in this equation, we will get the answer as minus 1 by 2 g tau square, then 4 times, then 9 times, then 16 times, then 25 times, then 36 times. Okay. If we take minus half g tau square as y naught, the position coordinate after first time interval, then third column gives the position in the terms of y naught. So we are just converting this minus half g into y naught. Okay. Therefore, the equation, this expression becomes 0 y naught, 4 y naught, 9 y naught, 16 y naught, 25 y naught, 36 y naught. Okay. The fourth column gives the distance traveled in successive s. So now what does it mean by successive s? So basically what the diagram which I just made, so it was for x1, it was for x2, it was for x3, right? But as we are first of all calculating the value of, so this y, this is your y, this is your y1, and this is your y2. So to calculate the value of x2, what you will do? Will do y1 minus y. Similarly, to calculate the value of x3, what you will do? y2 minus y1. So that thing is only been done here. So when you will do this thing, what you will basically do? For this location, you will do 4y minus y naught. For this, you will do 9y minus 4y naught. For this, you will do 16 minus 9. Okay. So when you try to do this everything, 4y minus y naught, 9y minus this, keep on writing everything. Finally, you will get the answers in successive intervals like this. So basically that x1, x2, x3, x4 values are y naught, 3y naught, 5y naught, 7y naught, 9y naught. So these are at the same time interval it is happening. At the same time interval, at the successive time intervals, the amount of distance traveled will increase. Okay. Okay, so now we find that the distances are in the simple ratio of 1:3:5:7:9:11. Quite evident, as you can see, that the ratio of distance traveled is 1,357,911. Okay. This law was established by Galileo Galilei, who was the first to make quantitative studies of free fall. Okay, he was the first one who made the quantitative studies of free fall, and hence this law is also known as Galileo's law of odd number. Okay, so that is how we understood this complete concept, as in why this ratio of, as in why this, just 1 minute, as in why this complete ratio is, so that is how we understood how this complete ratio is coming. Okay, so it is 1:3:5:7:11:9:11, 11:30, etc. Right? So let's move forward. Okay. So a new concept called as stopping distance of vehicles. Okay, so just to give you a brief idea of how important is this chapter or how important is this concept, this is one of the concepts which you will understand if you take engineering in the future scopes of your concept, then this is one of the concepts which you will understand in civil engineering. So in transportation engineering, this is one of the very important concepts through which studies are being talked about, and that actually gets implemented in the real life. So you can understand from even 11th class, you can start the building blocks of understanding your future concepts. Okay, so that is how important these small basic concepts are. Right, so that was just a brief explanation. Let's start with the basic result, what is being asked here. So stopping distance of vehicles. Okay, so when brakes are applied to a moving vehicle, the distance it travels before stopping is called stopping distance. Quite clear, it can be understood from the name itself. So what is being said actually, let us say this is a car. Okay, it is moving on a road. Okay, with a velocity v. Let us say the brakes are to be applied. What will the brakes do? It will provide a negative acceleration. That negative acceleration will lead to this velocity to be equal to 0. So this distance it took is nothing but called here stopping side distance, also called as SSD. Okay, fine. Those are definition. So stopping side distance of vehicles is nothing but when the brakes are applied to a moving vehicle, the distance it travels before stopping is called as stopping distance. Okay. So it is an important factor for road safety on the initial velocity V0 and the braking capacity or deceleration minus A, that is caused by the braking. Okay. So on whatever factor it depends upon the initial velocity V0 and the deceleration A minus A, which is caused by the braking. Derive an expression for stopping sight distance of a vehicle in terms of V0 and A. Okay, so basically we need to find a relation between this distance. What is this distance? This distance is nothing but displacement, which would be a function of V0 and A. Okay, let's start. So let the distance traveled by the vehicle before it stops be ds. Okay, so if I try to explain using a diagram, let us say this is that vehicle. It moved from this location to, let's say, this location. Okay, let's say we are taking this distance ds. The velocity was v equal to some v here, and the velocity v naught is equal to v here, and v final is equal to 0 here. Correct? Now, using the equation, v is equal to v naught square plus 2ax. Okay, we know that the final velocity is 0, so it's 0 is equal to v naught squared plus 2 into, please remember, a would change to minus a because it's a deceleration question, into the displacement in positive direction, so it's plus x only. So this will change to v naught square equal to 2ax, or we can write x is equal to v naught square by 2. Okay, so thus the stopping distance is proportional to the square of the initial velocity. Quite evident. The stopping distance x, which is nothing but also called as SSD, is proportional to initial velocity square. Okay, because acceleration is constant. You always assume that acceleration is constant in this explanation. Okay, so the stopping distance is proportional to the square of the initial velocity. Doubling the initial velocity increases stopping distance by a factor of 4. Quite evident. If we change this v0 to 2v0, so this will be the x would change it to 4x. Okay, so that is how this thing has been explained. So for the car of a particular make, the braking distance was found to be 10 meters, 20 meters, 34 meters, and 50 meters, corresponding to velocities of 11, 15, 20, and 25 meters per second. Okay, so as you can see that as the velocities are increasing, the value of displacement is also increasing, and there is a very small increase also. It is increasing very fine. So which are nearly consistent with the above formula. Stopping distance is an important factor considering setting speed limits, for example, in school. So that is one of the important important factor which we consider when we try to set the speed limits. Okay, one of the examples given is your school zones. Okay. Fine. Now let us understand this using one more example, that is reaction time. Again, as the name suggests, what is reaction time? So when a situation demands an immediate action, it takes some time before we really respond. Reaction time is the time a person takes to observe, think, and act. Okay. For example, you can understand this clearly using an example. For example, if a person is driving and suddenly a boy appears on the road. Okay, let us say this is a car. Okay, and the boy suddenly appeared, right? Your vision would have been till some place only. As you keep on driving, you will at some location you would see, yes, okay, so a boy would have appeared in your vision. Okay, so now what you will do, you will try to apply the brakes. Okay, so the amount of time it required to view the boy, think about applying the brake, and actually applying the brake is the reaction time. Fine. For example, if a person is driving and suddenly a boy appears on the road, and the time elapsed before he slams the brakes of the car is the reaction time. Okay, so you observed the boy, you think what you think about, you think about applying the brakes, and finally you applied the brakes. So that is a complete time you took, which is called as a reaction time. Fine. So reaction time depends on the complexity of the situation and on an individual. You can measure a reaction time by a simple experiment. Let us take this experiment, and that is the basis of this example here. So take a ruler and ask your friend to drop it vertically through a gap between your thumb and forefinger. This is how you have to keep almost a small support and try to ask your friend to drop this from this location. Okay, quite evident, and there is no force acting on it. This is also a case of a free fall only. Okay, where we were. So take a ruler and ask your friend to drop it vertically through the gap between your thumb and forefinger. After you catch it, find the distance d traveled by the ruler. So there would be some distance d. Let us say this, if we take this as location, so some distance would have occurred. Some this would have gone down. So some distance would have covered. So let us try to calculate a distance d. In a particular case, D was found to be 21 centimeters. Then estimate the reaction time. So what was the reaction time you took? So that you understood, yes. So he dropped it. You observed that he dropped. You thought about catching the ruler, and then you pressed your thumb and forefinger. The time it took for the complete portion is basically a reaction time. Okay, so that reaction time can be understood using this value of D given. Okay. So let us see. So the ruler drop in the free fall. So that was a basic consideration we can observe from the given data. Here again, the initial velocity is 0, which is v naught is 0. A is nothing but minus g, quite evident. So let us use simple relation, that is d is equal to d naught plus v naught t plus half at square. So d is nothing but initial displacement is 0 plus 0 minus half gt square. Okay, so that has only been written here. So just putting those values here, what you will get? You will get as the displacement. Remember, now see, now this is very important. This displacement value can also be written as minus d. Why? Because as you can see that the displacement is occurring in downward direction. Correct? Therefore, this will be minus d is equal to minus half g tr square. This minus gets cancelled. So you get tr is nothing but equal to under root of 2 d by g second. And the value of d is 21, so it will be nothing but equal to 0.21 meters. But the value of g is 9.8 meter per second square. And then you will get the reaction time is 0.2 seconds. Therefore, if you try to do this and the value of d, which was calculated was 21 centimeter, then your reaction time is 0.2 seconds. Okay. So given d is 21 centimeters and g is 9.8 meter per second square, the reaction time is nothing but your tr, which is equal to under root of 2.21 second upon 9.8, which is approximately equal to 0.2 seconds. Okay. So that being said, we are only left with relative velocity now. So this will be, let us close this lecture here only, because this is a new concept. Okay, or else we can start it, we can understand the basics, and then we can move forward with the examples in the last lecture of this lecture series. Okay, so let us start with relative velocity here only, so that I can make you understand the basic concepts. We can even revise in the next lecture, and then we can move on. Please try to understand this at a very greater depth, because relative velocity is required in the complete lectures of 11th class physics. Okay, relative velocity may be a little hard to digest some sort of in some ways when we go to 2D shapes or when we go to higher calculations, but let us first of all go with basics. Everything with basics, if the basics are clear, we can understand the difficult topics also. Okay, so let us start with relative velocity. Okay, yeah. So relative velocity, as the name suggests, relative as in with respect to something. Okay, so when I am trying to understand velocity, or let's say a train, if we are trying to find the velocity from a train, then the velocity with respect to train and velocity with respect to me may be different for something which is observed. Okay, so that is how this concept of relative velocity came into picture. Okay, so let us try to understand this complete chapter, complete subtopic. Okay. So you must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. So that is thing which is explained here. So let us say that we are in this train VA and we are being overtaken by another train. So this would have been somewhere below, backward, and then it was moving forward, and then it reached ahead of us. Okay. So we have experience of traveling in a train being overtaken by another train moving in the same direction as you are. While that train must be traveling faster than you to be able to pass you, it does seem slower to you than it would be to someone standing on the ground and watching both the trains. Please understand this line very carefully. Okay. While that train must be traveling faster than you to be able to pass you, it does seem slower to you. Then only relative, only it's all about relative here. Okay. So it does seem slower to you than it would be to someone standing on the ground and watching both the trains. Okay. So you would think that okay, the speed is not that much fast, but if you will be on the ground, then this would have looked very, very fast. Okay. So, so in case both the trains have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. Quite evident. You would have observed this also. If both are going at the same velocity, then it would have occurred. Let us see, we are not looking at the ground. If we are looking window to window, it looks like that both the trains are at stop or at rest. So in case both the trains have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. To understand such observations, we now introduce the concept of relative velocity. So that is how, or that is why we understood or we introduced a concept called as relative velocity. Let us try to understand this. Okay. So consider two objects A and B moving uniformly. Please remember it's moving uniformly with average velocities VA and VB in one dimension, say along x-axis. Unless otherwise specified, the velocity is mentioned in this chapter are measured with reference to the ground volume. Okay, so if it is not specified, everything is with respect to ground volume. Okay, so every time VA is equal to VAG and VB, it is just a method of writing this. Okay, so VBG. So G is with respect to ground, A also with respect to ground. Okay. So if XA0 and XB0 are positions of objects A and B respectively at some time t is equal to 0, their positions XA and XB at some time t are given by. How to calculate this? So this is nothing but XA is equal to, so because we are understanding that there is no acceleration happening, right? So it is moving uniformly with average velocities. Okay, that what means we know that X is nothing but equal to X naught plus B naught t plus half AT square, right? As A is 0, so this can get removed. So this is nothing but X at some time t is nothing but X at time 0 plus the velocity V, which is at A times t. Similar thing can be written. So this is for XA, this is for XA. Similar thing can be written for B. So it's XB into t, which is equal to XB times 0 plus velocity at some time B into t. Fine. So this is the only thing which is written here. Okay. So XA of t is equal to XA of 0 plus VAT and XB of t is equal to XB of 0 plus VB of t. Okay. Then the displacement from object A to object B is given by, so what is this? So it is nothing but XBA of t. So this is how relative velocity is being explained. Okay. So how it is explained? XB of t is nothing but equal to XB of t minus XA of t. Okay. So the first thing is written here. The second thing is written with a difference. Okay. Put those both values here. What you will get? This is equal to XB of 0 minus XA of 0. This B will be in subscript here. Okay. Plus VB minus VA of t. Okay. So last equation is easily interpreted. It tells us that as seen from object A, okay, as seen from object A with respect to object A, object B has a velocity VB minus VA because the displacement from A to B changes steadily by the amount VB minus VA in each unit of time. Okay. So that is the explanation from this expression. Okay. So we say that the velocity of B, now this is the definition. Okay. This is the mathematical definition of relative velocity. We say that the velocity of object B relative to object A is VB minus VA, or also written as VBA is equal to VB minus VA. Okay, so that was the definition of relative velocity. Let me stop it with this definition only. We will continue this discussion about relative velocity in the next class. Okay, so the course progress for you. Okay, so the course progress for you. We started the introduction, then we went on to understanding the position, path length, and displacement. Then we understood average velocity and average speed. and we understood instantaneous velocity and acceleration. And finally, we are on the last topic, that is kinematic equations for uniformly accelerated motion, which is completed. And finally, we have also started relative velocity. In the last and final class, we will understand relative velocity and do some problems. Finally, summarize the complete chapter, and that will be the end of motion in a straight line. Right? So, thank you for listening, and that will be the end. Let's meet in the next.